Okay, for question 1, the speed of a wave in medium x is greater than the speed of the wave in medium y. Which diagram shows the correct refraction of the wavefront at the boundary between x and y? Okay, well, if you look at the waves, they're traveling from a medium in which they go quickly to a medium in which they travel slowly, which means that the side of the wavefront that enters the slow medium, which is medium y, is going to slow down first and get left behind. Also, the wavelength, as it moves into the slower medium, is going to get shorter because the waves that haven't entered yet are going to catch up with the waves that already have. So it's going to bend towards the normal, and it's going to get shorter, the wavelength. And so B must be the correct answer. Okay. Question 2. Which of the following is true about boiling and evaporation? Boiling occurs throughout the liquid. That's true. So it's got to be either A or B. And evaporation occurs only at the liquid surface, so it's got to be A as the answer. A solid of mass m is initially at temperature delta T below its melting point. The solid has specific heat capacity C and specific latent heat of fusion L. How much must be transferred to melt it completely? Okay, so delta Q here has got to be equal to the Q of heating the solid, and then plus Q of melting. Okay, so that's going to be equal to mc delta T plus ml. And which one is that? That is D. Okay. Number 4, for a body undergoing simple harmonic motion, the velocity and acceleration are always in the same direction. That's not right. So we know that the definition of simple harmonic motion is when the acceleration and displacement are proportional to each other and in opposite directions. So if we look at the object swinging, so let's just consider this. We have it swinging from there to there to there and back, right? So it goes like this and then back like that. Okay, as it swings towards the middle, so as it swings towards the middle from the left position, it's going to be accelerating to the right and its velocity is going to be to the right. As it swings on towards the far right position, its acceleration is in the opposite direction to its velocity. And then as it swings back towards the middle, it's going to be have its velocity in the same direction. And then as it swings up towards the end, it's going to be in the opposite direction. So it's two quarters of the cycle. It's going to be in the same direction. So it's not a quarter of the period, it is half the period. 2 quarters is half. Okay, next question. 2 loudspeakers, L1 and L2, emit identical sound waves. Okay. The waves leaving L1 and L2 are in phase and are observed at points P and Q. The wavelength of the sound is 0.6 meters, and the distances are shown in the diagram. Which of the following is true? So in the central one, at this Q, we know that the path difference is equal to 0.3 meters, which is equal to lambda over 2. So that therefore it's a node. So it's going to be quiet there. Here we have path difference is equal to 0.6 meters, which is equal to a wavelength. So therefore we have antinode. Okay, and so let's have a look. Intensity at P is going to be minimum. So it's either this one or this one. Intensity at Q. Oh, sorry, what am I saying? That's not right. I got them confused. So the intensity at P, that's where the path difference is a whole wavelength. Those places there's going to be constructive interference because that's an antinode. At Q, we have a half wavelength path difference, so there we're going to have a minimum, and so B is the correct answer. Which of the following correctly relates the direction of oscillation of the particles in a medium to the direction of energy propagation for transverse and longitudinal waves? Okay, so in a transverse wave, the direction of oscillation and the energy transfer are perpendicular, so it's got to be one of those two. And in a longitudinal wave, the oscillation of particles are parallel to the direction of energy transfer, so it's got to be B. Each of the resistors in the arrangements below has a resistance R. Each arrangement is connected in turn. In which arrangement is the current the greatest? So what we want is to have minimal resistance. That will occur when we have all the resistors in parallel. And so C is the best option. Because that's where there are the most possible pathways for the current to take. And there are no real bottlenecks in that. By the way, you can work that out. So in this case, R is equal to 4 over R inverse. So we get a quarter of R. In this one, we have R is equal to 4R. In this one, we have R is equal to 2R for the two resistors in series, plus 2 over R inverse. Okay, so that's definitely bigger than the option that we chose. And in D, we have R, is equal to, we got two parallel bits, so we got 2 over R times 2, basically. And so option C will give the smallest possible resistance and therefore the greatest possible current. Two identical waves of wavelength lambda leave two sources in phase. The waves meet and superpose after traveling different distances. What path difference will result in destructive interference? Okay. A path difference of lambda over 2 is what we want. Yep, so this is what we want. That means that they'll be out of phase and they will interfere destructively, which represents the pattern of electric field lines of two small positive point charges held at the positions shown. Okay, two small positive point charges means that they will repel. We have field lines coming out of both of them everywhere. So it cannot possibly be A or C because we have field lines going into the positive charges. So that's absolutely false. Okay, we know that there will be zero field in the middle there. B has to be the answer. Okay. The other reason we can eliminate D, by the way, is that this field line has this field line is going in both directions at once. So here, that can't happen. Field lines point in one direction. They always start at a positive charge and end at a negative charge. And if there's no negative charge around, they all kind of go out to infinity. Okay. So two resistors of resistance 10 ohms and 20 ohms are connected in parallel to a cell of negligible internal resistance. Okay. The energy dissipated in the 10 ohm resistor in 1 second is Q. What is the energy dissipated in 1 second in the 20 ohm resistor? Okay, so here, both get the same voltage. So we really want the power, right? So power, that's resistance. Let's get rid of that. Power is equal to current times voltage. And we know that the voltage is going to be the same for both. The current's going to be different for both. But what we're given is a resistance. So we know that I is equal to V over R. So we can substitute that in. So that's equal to V squared over R. And so if the 10 ohm resistor, so P10 is equal to V squared over 10, and P20 is equal to V squared over 20, which is only half of the power of the 10 ohm one, because the voltage across each parallel branch must be the same, and because the resistance in the 20 ohm branch is double, we're only going to get half of the power, and so the power output of the 10 ohm one was Q, so half of that is Q over 2.